Hey there, my name's Gary Sims and this is Gary Explains. Today I want to look at Docker, which means we're talking about containers, and I want to do that using a Raspberry Pi 4 because it now of course comes in models with 2 gigabytes and 4 gigabytes, and I thought using a 4 gigabyte version of the Raspberry Pi 4 would be a good way to try out the capabilities of this board and also to look at Docker. Okay, so we're talking about containers. Now, containers are different to virtual machines. With a virtual machine, for example, you would have here, it shows here a hypervisor. This might be something at the OS level. It might be a program, let's say, like VirtualBox. And inside of it, you can run entire operating systems where the whole machine is emulated. So the graphics cards and the sound cards and the network cards and the CPU and the motherboard. And when you run a guest operating system, maybe you could run Windows, you could run Linux, you could run FreeBSD, and everything that's running in there, it actually thinks it's a real machine. It just happens to be done in software in cooperation with the underlying hardware. However, with a container, you actually don't virtualize the operating system. What you do is you abstract the user environment. So that means things like the command line and the libraries and the files that are part of the operating system, they can all be put into different self-contained packages, which we call containers. So it's not a virtual machine. Now, because they're just really replicating only the user end of the whole thing, then they actually are much more lightweight. So in app A, you could have maybe Java running. In this one, you could have kind of Node.js. In this one, you might have something else to do with network monitoring, and they all run in their kind of independent packages, but underneath, using the Docker engine, they interact with the underlying operating system to get access to different things like files and so on. And because we're talking about containers, of course, you have to have an obligatory picture of a container. And so I dug one off one of the royalty-free websites, and there we have a lot of containers. But of course, the idea is that with a container, everything that's in the container, once you shut the door, it's all self-contained, and you ship it about on a lorry or on a ship, on a cargo ship, but actually what stays in the container is always the same until finally you open the container and sort of unload it. And it's the same with the idea with a container on Linux, for example. Everything you need is inside the container, and you can have it on Windows, you can have it on Linux, you can have it on ARM, you can have it on x86, but actually everything you need there is inside the container itself. Okay, so to start off with, we need to install Docker. Now, this command here is the normal way to do it. That's how you would normally install Docker, and that automatically detects your operating system and runs. So that's good for basically all kind of versions of Linux. However, Docker is not yet officially supported on Debian Buster, which is the version that is using with Raspbian that ships with the Raspberry Pi 4. So there's a workaround here, and what you need to do is you need to run the first part of the command, so it gets the docker.shell file. Then you need to edit this docker.shell file, and you need to, where it says here 9, and I've given you a few lines of code there, you need to change it to 10 because that's what Buster is, but you still tell it it's using stretch. And then it will go ahead and install the packages, and they're all compatible, it all works. So if you're doing it on a Raspberry Pi 4, you need to do this hack. If you're doing it on a Raspberry Pi 3 or on a Linux machine on Intel, then you don't need to worry about this. You just need to run this normal Docker command like that. Okay, so what we're going to do now is we're going to go over to our Raspberry Pi, and we're going to start running some commands. And the first command we're going to run, very simply, is docker -- version. So here we are over on my Raspberry Pi machine, and so we're going to do that docker -- version, and there we can see that we're running Docker 18.09.0, and there's the build number. Okay, so the next thing we want to do is actually run a container. Now, they ship it with a very easy container, which is called Hello World. So what you do is you say Docker. That's always, all the commands start with Docker when you're interacting with the Docker environment. Run, well, that's pretty obvious because you want to run something. And then the default container they give you is called Hello World, just like it would be if you were writing a program in C or Golang or Rust or whatever. You always write Hello World first. And so when we run this, actually it fires up this container, and it says, look, hello, you've actually managed to run this container. Well done. It will run it for yourself. And it says, why don't you try something more ambitious? And it gives you the command here, run this. So we're going to do what it says. We're going to run now not just Hello World, we're going to run the Ubuntu container. So we're going to take exactly that command. Few things to notice. We're saying run again, yes. The I and the T basically makes this interactive. It means you can talk to it via the command line, which of course what we want to do. We're going to run Ubuntu, and it's making sure that we run the bash shell in Ubuntu, and we're going to change this here at the end in a minute to show something else that you can run. So let's run Ubuntu bash. And now, this is why I did this. I wanted to say it doesn't find Ubuntu because I haven't got the Ubuntu container. So it will automatically download it for us. That's absolutely brilliant. So this is now going to go off to a repository of containers, and it's going to download Ubuntu. And we'll talk more about that repository of containers in a moment. So let's just wait for this download to finish. Okay, so the download is finished, and we can see now that we are here in this as a root connected to this machine. We've got the hash sign there. So we are actually now running inside of a Ubuntu system. Now, although this is running on Raspbian on the Pi, actually this looks like a Ubuntu system. In fact, if we do more /etc/os release, it says, oh, look, you're running Ubuntu 18.4.02. But interestingly, of course, if we do an ls CPU, it still tells us that we're running on the Cortex A72 because we are running on the Raspberry Pi. If we run, for example, top, we will see that we have kind of, the 4 gigabytes of memory here. But this is why containers are so great. Look at this, hardly any processes running, just the processes that we need, not all those processes that are running as part of running a complicated operating system, actually just this user land stuff that we need to be running here. And finally, if we do a uname -a, actually what we'll notice here is this is not the Ubuntu kernel. This is actually the same kernel as we have on our Raspberry Pi. And if we go over to this other window that I've got here, also logged into the same machine, if I do uname -i, we can see we can do exactly the same thing. We can see here 4.19 GNU Linux ARM, exactly the same. The only difference here is the host name. This is this virtualized, this containered system here, and this is where it says Pi because that's actually the name of my Raspberry Pi. Okay, so to exit out of the container, before we do that, I just wanted to do one thing. I want us to go to user/source, that's just a directory here, and I want to just create a file. Okay, and we're just going to call it none.txt. Okay, now this will be important later on, but okay, so to exit out of the container, what you do is you just exit out normally. You can press Control-D or type exit, and out we come, and we're now back to our normal Raspberry Pi underneath. Now, if we now run the same command, but we change the bash for top, what this shows is we can actually run a container and run a program directly. So in this case, I want to run the top program. We're not going to interact with it using the command line. It's going to go straight into running that top program. So if we fire that up, it will start up the container, and there it is. It's just running top, and it tells us about the CPU usage and the memory usage. And so what this shows is the containers are very good at running specific commands, and we're going to get into this, how you can make it run your own programs that you want to do to run your own environments, the own apps you're developing inside a container. And now when we press Q to quit out of that, it actually exits out of the container completely. So the container there disappears. Now, we were just talking about the different images. Let us just say one thing. If you do Docker images, it will list all of the different images that are available. So there's Ubuntu that we downloaded. There is Hello World. And there's some other ones here that we're going to use. And I've pre-downloaded them to make our video quicker. So we're going to be looking at GCC in a minute. We're going to be looking at Node in a minute, and so on. So let's now just say that you can go over to the Docker website, and there is a hub of all the different images that are available. So it's called hub.docker.com, and if you go over to browse popular images, you can see all the different images, not just Ubuntu. Look, the first one is Java, MySQL. Then you've got, this the official build here for network monitoring, BusyBox, Mongo, Ubuntu there, Alpine Linux, Node, which we're going to use in a minute, and then the list just goes on and on. So there are lots. In fact, I think I saw a thing here at the top. There we go. Look at that, 2.5 million images are available. Now, there's one thing to notice. When you do pull down images, you've got to be careful who you're pulling it down from, because you don't know what people have put inside that image. So it can be a potential security. Here we have, of course, verified publishers. We're trusting that Oracle are shipping good images. There's also official images that come from Docker themselves. So that's important. If you just pull down an image from somewhere, you don't know what that person has included and what they're kind of doing in the background. Just something to be aware of. Okay, so now back onto our Raspberry Pi. Now, you notice that when we ran that command with Ubuntu, we went into user source and I created that file. If we go into this now here, you will see there is no file. That file does not exist in this directory. So when you fire up a container, actually what happens is it creates a unique container which it runs for that moment until you exit it, and then when you run up a new one, you spin up a whole brand new container. However, the good thing is the old files are still there. So if you do want to go into an old one, what we can do is we can say docker container ls, which is Linux, Unix for listing things, -a, all of them. And here we can see these are the different ones that we ran. Here was the Ubuntu, the Ubuntu, the Ubuntu, and these have IDs connected to them. Okay, and there's also the hello world there that we ran earlier on. So what you can actually do is you can restart one of these old ones. So what we're going to do now is we're going to say docker, and we're going to say start -i. Now this is the one here. Look, we've got, that was the first one I just ran a second ago that didn't have the file in it. This is the one where I was running top, and then this is the one where we ran bash first of all. So we're going to say please run that one, and what that will do is it take exactly the same files and restart that container. And now if we go into user source, we can see that file's there. So there's two things to remember. First of all is that the container files can be still around if you want them to be, but generally when you start a container and then you run it, it's unique for that moment. All the stuff that goes on there is unique, and then it goes away. Of course, if you want to keep log files or you want to analyze crashes, then you need to keep these around so you can find out what went wrong. If they all get deleted, then that might not be helpful when you're trying to do debugging. However, if we exit out of here, if you want to get rid of all the old ones, what you can do is you can say docker container prune, okay, and that will get rid of all those old images. So if we now do docker container ls -a, there's nothing, they're all gone. And you can run that same container here, Ubuntu in this case again, but if you include --rm, then what that does is as we're running this file here, once we exit out of it, the files are automatically deleted. So if we do, again, to list the files, there are none there now. So including that --rm will actually make sure that the files associated with that container are always deleted when the container exits. Okay, so now I'd like to talk about a thing called a Dockerfile. A Dockerfile allows you to create a container that has got some predefined stuff going on inside of it. So it's not just vanilla Ubuntu, it's not just vanilla the Java container. You can actually put your own stuff in that container and get your own stuff to run in the environment that you've chosen. So Dockerfile defines what goes on in the environment inside your container and allows you to build your own app into your container. And so here is an example of a Docker file, and you can see it's fairly easy to understand. The from part here says that this is based on the GCC, which is the C compiler from GNU. This is based on GCC 4.9, so you can always make sure you get the same version of the compiler as new versions come out. And to create this, what you've got to do is you've got to copy everything that's in our current directory into a directory called my app in the container. Then when the container is running, the working directory will be that my app directory. And in preparing the container, it needs to run the compiler for a program called hello.w.c. And then when you run the container, it will run .hello. So what we need to do now is if we go, I've got a directory here called hello world GCC, and inside of it there are two files. One is the Docker file that I've just showed you, and the other is the hello world program. So there are two files in here, and when we build the container, it would take that hello.w.c file and copy into the container and then actually compile it to create that program. And the way you do that is you use this command docker build, because obviously we're not running now, we're building a container. T for tag, I'm going to tag this as hello world GCC, and I want you to do everything that's in this current directory, which is the directory with the Docker file in it. So if we now go ahead and build our own file, there you go, it's done that, and even as you see here, it's run GCC. Some of this is cached because I've done this before, but it goes through that and actually run it. And if we now, as we did earlier on, I went over it quickly, but if you look at Docker images, we can see here hello world GCC because I have that built now. And now we can run it. So now we can, just like we ran the Ubuntu, we can run our own version of this now. And we can say Docker run hello world GCC. And what does it do? It runs that program, hello world, hello from within a Docker container. So now what we see is actually we can write our own program in C, in Rust, in Golang, in Python, in whatever you want to write it in. You can put it into a predefined environment, you can build it and you can run it. And then you always know that whenever you run your program, that container will always have the same environment, which means it's much safer rather than you go from one machine to another and you don't know the configuration, you don't know what they've got installed, are the right packages installed, is the right file system there, is there enough, and all the things that you want to check, are the right libraries installed, is everything there? Now it's all there because it's this predefined environment that you have control over. Okay, let's have a look at another example. This time I'm going to be using node.js. So I'm saying from node. Same thing again, copy and working directory into this folder called my app. A new command here, expose 80. So that's saying that this container needs to use port 80. And of course, port 80 is what we do for HTTP. So when you connect to a website, inherently it's connecting to port 80 of that server. And then we're saying when you run the container, please run node and run index.js. Now, what's index.js? Well, let's have a look. It is basically a very, very simple and stupid in one sense web server that whatever request it gets, it's going to say hello node.js server here and the date and time. Even if you ask for a graphic file, even if you ask for an icon, it's still going to send the same thing. So this is basically completely hopeless when it comes to actually doing anything real world, but it shows us that we can run a web server and run that web server inside of a container. So let's do that. So here we are back on the Raspberry Pi. Now I'm going to go into a directory called node web server, and inside we've got our Dockerfile, which I just showed you, and there is also this index.js file that I just showed you. And again, we can now build that so that we actually get a proper container using these files. And of course we use the build command, build, and then here -t for the tag simple web server, and then everything in here. It's gone ahead and built that. And the same thing again, we can run it. Now there's a couple of things to notice about how we're going to run this. Okay, first of all, notice this here. I'm using the --rm. Okay, but notice this here, -p4080. So what this is saying is port 80 in our program, in our web server, gets mapped to port 4000 on my Raspberry Pi. And that means that there is now a unique mapping between this container at port 80 and the Raspberry Pi, because obviously I might have something else running on my Raspberry Pi at port 80, and also some ports are privileged. So this port here means if I now connect to port 4000 on the Raspberry Pi, I'm actually connecting to port 80 on the container. So it maps from the real world Raspberry Pi through to the container. So if we run this now, it's going to come up and say I'm listening on port 80, but of course it's actually listening on port 4000. So let's get a web browser out and going here. Now the address of my Raspberry Pi is 1.44, which I've got here, and I'm connecting to port 4000. So if I now connect to port 4000 on my Raspberry Pi, what do I get? I get a response from my web server written in node.js. There you go, and the date and time. So I can refresh this as many times as I like, and I'm now actually connecting to a web server that's actually running inside the container on my Raspberry Pi. But here's the interesting thing, because we're running this in container, I can run a second one. I can run two web servers now. So I can now actually run exactly the same command, the simple node web server, but notice the difference here. Now I'm going to say map port 4001 to port 80. So I'll have one web server connecting on port 4000 and another web server connecting on port 4001, and both web servers think they're working on port 80 because of course that's the standard port number for a web server. So here on the second window for that Raspberry Pi, what we can say now is that Docker command that I showed you for running the second web server. So we do that and we're going to run it. And so notice now it says I'm listening on port 80 because it's a container. It thinks it's in its own little contained world, a contained environment. But actually they're both listening on port 80, but they've been remapped. So let's get the web browser again. So here is the URL, but rather than 4000, we're going to say 4001. And now we actually see that we have the second web browser we're applying to. So here we have one from the first web browser, and here we have it from the second web server. So these two web servers are now running independently in their own containers, and we can expose them through to the real world using Docker and access them on different ports. Okay, so there you have it, an introduction to using Docker on a Raspberry Pi 4. Now this really is just an introduction. There's loads more stuff to do with services, swarms and stacks. Then there's Docker orchestration using things like Kubernetes. Now if you are interested in more Docker tutorials, please let me know in the comments below, and we'll see whether it is worthwhile doing a follow-up video. But otherwise, go ahead and try that on your Raspberry Pi 4. You can even try it on a Raspberry Pi 3. It really is a good way of experimenting with containers. Okay, that's it. My name is Gary Sims. This is Gary Explains. Really hope you like this video. Please do like. Please also subscribe. And well, that's it. I'll see you in the next one.